Hello everyone, welcome back. I'm Alok Kumar, and today I would be doing mean value theorems. We would also be doing some applications of it. And as anyone who has seen the previous JE papers, all of you must be have noted that this particular topic sees a lot of questions. So it's very important to be well versed in this topic. So let me now share my screen with you all and start the lecture. Okay, so first of all, let us do one statement that will tell us that how the theorem is explained. Okay, that's fine. Now let f ab to r, let f ab to r, ab closed, be a function. So this is a function. This is a function. So I should write if f ab to r is a function. So if this be a function such that first is that f is continuous, f is continuous on a comma b. So that is closed interval, so continuous on a comma b, that is closed interval. Second, f is differentiable, on a comma b, that is open. So let me remark that you require continuity on a closed interval, but differentiability you require only on open interval. So if the function satisfies such, so f is such that it is these two. And third, that f of a equals f of b, that is that you require that f values at endpoints are equal. Means function has same values at endpoints. So if these three conditions are met, this is the hypothesis satisfied, then there exists some c belonging to a comma b open. Means there is a point c in the interval a comma b open satisfying f prime c equal to 0. Anyway, we know f is differentiable. So what we are saying is that if f ab to r is a function such that f is continuous on closed interval ab, mind you, closed interval continuity, f is differentiable on open interval ab, and fa is equal to ab or fa equals ab, that is f values or the values that the function takes at endpoints are equal, then there exists some c, or there is a c belonging to a comma b open satisfying f prime c equal to 0. Means there is a point c such that the derivative is 0. This is called as Rawls theorem. This theorem has been named as Rawls theorem. This is known as Rawls theorem. It's one of the cornerstones of calculus. Many more theorems, the later one, can be derived by applying Rawls theorem to some particular function. So it is of utmost importance. Now, there is one geometric meaning also here. So geometric meaning is like this, that suppose you have got a random curve. Suppose I draw a curve like this kind of thing. So if f of a, so this is a and this is point b. So this height f of a, this height f of a and f of b, this is same. Means if I write point f of a, I have not shown the y-axis, not needed, afa and bfb. So if you are saying that fa equal to fb, means there are points a and b on the curve. What kind of curve? That is explained out, or that is spelled out by the hypothesis. This says continuous on AB. Means the graph of f is continuous. So you can draw the graph, say, without taking your pen off the paper. And so this is your graph. That graph is continuous graph. And the graph is such that it is smooth. Means it has no sharp corners. Formally we say that f is differentiable means f has a tangent at each point of the graph between a and b, except possibly and a and b itself. Means a and b are excluded. So you require that f has a tangent. So you require that f is continuous, means you can draw the graph, and f has a tangent. So f has a tangent. So graph of f has a tangent at each point between a and b, except possibly at b. A and b not counted. A, b not counted. Means the graph has got a tangent, so it is smooth in absence of sharp corners, so it is differentiable. Then the theorem says that f prime c is 0. Conclusion: it means that there is a point on the curve at which the tangent is horizontal to the x-axis, in fact the line AB, which is also horizontal. So it says that there is a point C, some point will be there, so the C point, which coordinates are given by C and FC. So they are saying there is a point C such this is 0. There may be more than one such points. That is fine. It says there exists a C, means at least one C, some C satisfying this one. So it means this is called the geometrical meaning of Rolle's theorem. Of a special application in JE is its polynomial thing. So what we do that, suppose f of A equal to f of B is 0. What is good about 0? The good thing about 0 is that now these numbers A and B are roots in relation to f, or roots of f. Roots in relation to f, or simply roots of f. Means the numbers where f vanishes, f and fb, they are called roots of f. And so we can say that if f is a differentiable function, we can say if f is a differentiable function. So if f is a differentiable function on, say, R, I am taking on R, like polynomials we will take. Polynomials indeed are differentiable on whole of R. So if f is differentiable on R, then fa equal to fb equal to 0 will imply that f prime c is 0. Means between two roots of f, means between two roots of f, their edge, there is a root of f prime equal to 0. There is a root of f prime between two roots of f. So between two roots of f, there is a root of f prime. That conclusion comes from Rolle's theorem, because you are saying f and fb equals 0, so a and b become root. Especially in polynomials, we can say like this. I will write with respect to polynomials some conclusions. So some results. So some results we are writing results, and let me change the color. And so one is this, that let px be a polynomial. Let px be a polynomial, and suppose p has roots alpha 1, alpha 2, all the way alpha n, something. So p has roots alpha 1, alpha 2, and all these numbers are roots of p. So they may be repeated also. For now, I'm taking just, if they are repeated, they just one alpha will come here, right? We'll write it only once. So they are the roots arranged in order. So what this theorem tells you, that between, so it means all these numbers are such that p of alpha is 0. So you are saying that between two roots of p, polynomial, there is at least that same thing equal to, this is saying that there is at least, or there is one. One does not mean, or there is, I would say rather a, there is one also may be confusing a little. So there is a, at least means a. So then between two roots of p, there is at least one root, or there is at least one root, there is one root of p prime. So that is, we are saying about roots of p and p prime. So there is at least one root. What if you look at p prime? Suppose p prime has roots. Now beta 1, beta 2, beta 3, till beta, of course it must be n minus 1, so I will not write this number, maybe beta s something. P prime has some roots, beta s. So I let me write it, and this is beta s some number. So now from already we know that between two roots of p, there is at least one root of p prime. I want to ask the question in other direction, that between two roots of p prime, what can you say about roots of p? So I will answer it in a result, and I will write that between two roots. So better I will use that between two consecutive roots. So important, consecutive between two consecutive roots of p prime, there is at most one root of p. Mind you, this was at least. At least changes to at most. From p to p prime, you have got something like at least. So you expect that when you go from p prime to p, it is reasonable that at most words should come up. It does. So let me now put it formally. So formally it was that between two roots of p, there is at least one root of p prime. Now, if you know the roots of p prime, then I will say between two consecutive roots of p prime, there is at most one root of p. Again, this is equivalent to this statement, the above statement, or Rawls theorem, you say. Why? Because I will prove it by saying proof by contradiction. This is an important proof, important idea. Proof by contradiction. The way you prove that root 2 is not rational. So you start by saying that, okay, let root 2 be rational, and see what contradiction it leads to. Similarly, here we will prove that we want to prove that between two consecutive roots of p prime, there is at most one root of p. You negate it. You say no. So you suppose. So you assume. You assume to the contrary. You assume to the contrary that between beta 1 and say beta 2, between two roots beta 1 beta 2, they are saying consecutive beta 1 beta 2. So let me write it a little further so that we can accommodate more numbers. So between beta 1 and beta 2, this is p prime. So let me say that you are saying that between beta and beta 2, p has got roots, two roots, not one. So assume that, contrary that between beta and beta 2, p has two roots, say alpha m and alpha n, two roots. Some name as the alpha m, alpha n, two roots. Then Rawls theorem tells that between alpha m and alpha n, here, between this here, Rawls theorem tells you that because p has roots, so p prime has a root as a root here. Means there is some number beta such that alpha m less than beta less than alpha n, and beta is a root of p prime. So there is a root of, so there is some root beta of p prime comes here, but it can't happen because beta 1 and beta 2 are consecutive roots, so there is no scope for any other root in between them. So contradiction achieved. So we'll say that between two consecutive roots of p prime, there is at most one root of p. There is no need to add the word consecutive here, because between two roots of p, there is at least one root. Of course, between two roots which are not consecutive, there will be more. So no need to stress. So this is perfect true. Between two roots of p, there is at least one root of p prime. Here you have to add, otherwise it will be wrong. So here you are saying between two consecutive roots of p prime, there is at most one root of p. This really will help you that if you want to find roots of p, but roots of p you do not know, but roots of p prime you know. So from a knowledge of roots of p prime, you can climb up and you can find the roots of p, at least their number, that how many there are the roots of p. So a knowledge of roots of p prime can help you build the roots of p themselves. That's the importance. I will just review the proof once again. So the proof was based on this, that first the statement was that between two consecutive roots of p prime, there is at most one root of p. Proof by contradiction. Assume to the contrary. You want to prove at most one. Assume, no, not at most one, more than once, means two. Just negate it. So just negate. So mathematician tell that just negate it. So let me change the color and then write it somewhere. So you are saying just negate that. So just negate. Just negate. So negate that. You are negating. Means you negate this. Once you negate that, you are they are saying that somebody is claiming that there is at most one root. You say no, no, no. You are not telling the truth. Means negate it. Say not at most one, but two, at least two. So you are saying okay. Assume to the contrary that beta 1 and beta 2, between beta and beta 2, P has two roots. Say alpha m and alpha m and alpha n, the names. So say alpha m and say alpha n. Then between alpha m and alpha n, P has roots now. By Rawls theorem, that its derivative P prime will have at least one root between alpha m and alpha n. So it means P prime has a root between this, that is beta. It means P prime has a root beta between beta 1 and beta 2. P prime has a root beta between beta 1 and beta 2. But that can't happen because you promised that beta 1 and beta 2 are consecutive roots. So how come this beta is here? So it means contradiction obtained. So we will say between two consecutive roots of P prime, there is at most one root of P. Understand it very carefully. Okay, next we can say like this, that two more results. So already roots of P prime are arranged. So they are beta 1, beta 2, and then beta s. They are some arranged somewhere. Now you are saying that one is between two roots of P prime. There is at most one root of P, and then at most one root of P can be greater than the greatest root of P. Means at most one root of P can lie in this interval, can be greater than the greatest root of P prime. At most one root of, this is P, at most one root of P can be greater than the greatest root of P prime. So at most one root of can lie here, or for P. For P, here only at most one root will lie. Similarly, at most one root of P can be less than the least value, than the least root of P prime. Means in this interval also, P can have at most one root. P can have at most one root. So I'm writing this. P can have at most one root. And in between also, you know, this is all everywhere at most one, at most one, at most one. This is number of roots of P between the roots of P prime. So it means what you have got is very much fundamental, that you have said that if I arrange roots of P prime on number line, arrange number line, so from left to right, then in each of, suppose there are s roots of P prime, then you have got interval mode s plus 1. So it means you can say that okay, between in each interval that is got by partitioning these roots, in each interval you expect that P has at most one real root, at most one. And then by using intermediate value property IVP for continuous functions that we did that time on continuity chapter, we can actually prove, or we can actually find the number of desired roots for application part. So let me now take up one really challenging problem based on this one. If you have followed perfectly, then you should have no difficulty. So the problem says that find the set of all A element of R. So all, or I'll change this one. So I may say that this is this one, that find the set of all, say all K element of R, all K parameter, such that x to the power 4 minus 14x square plus 24x minus k equal to 0 has 4 real and unequal, means real and distinct, real and unequal roots. So we want to find the set of all K element of R, all K belonging to R, such that the 4-degree polynomial x to the power 4 minus 14x squared plus 24x minus k equal to 0 has 4 real unequal roots. See, such a problem if you see, then obviously we know only quadratic and at best cubic and a special type of quartic or biquadratic. So of course calculus will give you the way, Rawls theorem here. So we want the knowledge of, we want the knowledge about roots of, that's the motivation, roots of this one, f, say fx, roots of fx, I want roots of f. Now I do not know roots of f because k is there, so let me get f prime. So f prime equals 4x cube minus 28x square plus 24. That is your, this one, that is your f prime. It turns out that I can factor, so I will write 4x cube minus 7x plus 6. That is 4 times x cube minus 7x plus 6. That can factorize x minus 1. So let's do the background work. X cube minus 7x plus 6. You know that x equal to 1, if you put it vanishes. 1 minus 7 plus 6. X minus 1 is a root. And all through my lectures, I have told you this short technique, that to factorize, don't divide, just equate the coefficients. X can come only from x square. This is 1, it is 1, so this must be 1. That's all right. 6 minus is there, so it can be only of only negative 6. So negative 6 you can write. And this coefficient only have to check, call it a first. So equate coefficient of x square on both sides. Left side is 0, it is here 0. Here x square will come x square will contribute 1 is from a, that is, this is a, and 1 is minus 1. So a equals 1. And so you get x minus 1 and x square plus x minus 6. So x minus 1, x square plus x minus 6. You can still find that this is a root, x equal to 2 is a root of this one. So I can write x minus 1, x minus 2, and x plus 3. It means that f prime is factorized. That's really advantage. F prime is factorized. I'm happy. See, f was not. F was just something, x to the power 4 minus 14x square. But f prime is really nice in the sense that f prime gets completely factorized. So roots of f prime are known. So it means that now these are number line, and I am saying roots of f prime. Roots of f prime. So f prime roots are 1, minus 3, negative 3, then 1 and 2. They're the roots of f prime. Now these are your betas. Now between each root of f prime, between each root of each two roots, consecutive roots of f prime, so in each of these intervals, there can be at most one root of f. Means this is less than equal to 1 here, less than equal to 1, less than equal to 1, less than equal to 1. Means either no roots or either no roots or exactly 1. So everywhere it is no roots or exactly 1. Only these two possibilities, exactly 1. So in each of these intervals, I know that f can have these kind of things. All it is left to me to calculate. So compute or determine the sign of f prime. So sign of f. So let's me compute the value rather. So this is, so we will say that compute the values of f at these points, to determine the sign. I want sign, positive or negative. Of course it's not 0, positive or negative I want. So what I can do here, that now I can write like this, that all now get fx again. So fx was x to the power 4. Let me check. X4 minus 14x squared, you can say plus 24x. So your fx here plus 24x minus k. Now I will write x and here f of x. So x negative infinity, then negative 3, then 1, then 2, and then infinity. So already we know that at negative infinity, this sign is determined only by the largest power, x to the 4. So this sign is infinity, this value infinity, so this is positive. Here also infinity, it is infinity again, so this is positive. These signs are positive. F. Now f minus 3, if you calculate, compute, you will get 3 to the power 4 minus 14 into 3 squared minus 24 into 3 and minus k. So I will get 81 minus 339 and then 914. So I will get 126. So this is 126 minus 72 minus k. So I will get now 81 minus 198 minus k. So that is negative of 117 minus k. So I'm getting this value as negative of 117 minus k. I need this value. F1. If I write F1 is simple, no computation. F1 is 1 minus 14 plus 24 minus k. And that gives you 1 and plus 10 and minus k. So that's 11 minus k. So this is 11 minus k, that is f of 1. And f of 2, if I calculate f of 2 is again 2 to the power 4. So 2 to the power 4 minus 14 into 2 to the power 3 to the power 2 and plus 24 into 2 minus k. So let's calculate quickly. 24 minus 2 to 4. So this will be your 56 and plus 48 minus k. So that you will give, ultimately you will get here minus 8. This is 16. This 2 to the power 4 I can write as this is 16. So 16 minus 56 plus 48 minus k. And that gives you 8 minus k. So it's just a matter of following computations. So I get 8 minus k. So I have got all these numbers now. So it is positive here, positive here. Now, if you want f to have 4 unequal real roots, you know that it means in each of interval it must have exactly 1. Here exactly 1, here exactly 1, exactly 1, exactly 1, so 4 roots. So for that to happen, now you know something called intermediate value property, IVP, for continuous functions. Of course, polynomials are continuous on whole of R, so that's not to worry about. So intermediate value property, I said this one in the continuous chapter, intermediate value property for continuous function. We are applying one corollary here, that if f of a and f of b product is negative, then between a and b, means in the interval a b, this f has at least one root. At least one root. Now, at least one. Now, this is, so it means if I can ensure that this is negative and this is positive and this is negative, then we are done. Because positive, negative, one root, negative, positive, one root, positive, negative, one, and one, so forth. At least one. This is at least one. But Rawls' theorem tells you, or equivalent of it, at most one. That tells you at most one. This one, at most one. So at least one, at most one. So if you say at least one, and one direction it is at most one, they together will imply exactly one. That's the point. They will write exactly one. So it means it is enough, it is both necessary and sufficient that f at this point, f at minus 3 be negative, f at 1 be positive, f at 2 be negative. Then you will find that you will have 4 real and equal roots. So just we have to solve these 3 inequalities. So let me write here. This is minus 117 minus k. This we want to be negative. So this is less than 0. Then next value was 11 minus k. You want this to be positive, so positive. And next is 8 minus k. You want them to be negative. So now just solve and find intersection of them. This gives you k exceeds negative 117. This gives you k less than 11. This gives you k greater than 8. Intersection of them, if you take intersection, because they must be satisfied simultaneously, all at the same time. It's like and, this is and this one. So it means that you will find that 8 less than k less than 11. It means we have found that the set of all values of k such that f has 4 real and unequal roots are given by 8 less than k less than 11. So this is what we will find like this. So this this question has got answer as the set of values of k is 8 to 11. Now uh, IIT can phrase the question in, of course, more than one choice form or other form, or maybe like integer type. There the number of integral values of k for which this equation has four real and equal roots is. So number of integer values you want. It means that now you will say that okay, integers is 9 less than k less than equal to 10. So there are only two values, 9 and 10. So there are just two integer values, although number of real is infinite, but integer, there are just two integers for which this equation has got four real and equal roots. So this is it. Next we take up some more applications. So one more I take like that, again finding sign. So this question says that you are given f of x is 3x to the power 4 minus 8x cube minus 6x square plus 24x plus 1, and you want to say that you want to investigate rather there how many real roots. How many real roots does f have? Again, solution would come through Rolle's theorem. So we will write that roots of f I do not know. That's why so f prime will be 12x cube minus 24x square minus 12x plus 24. That is your f prime. So 12 I can take common, and this is x cube minus 2x square minus x plus 2. You would find that this equation x cube minus 2x square minus x plus 2 has x equal to 2 as a root. You can verify 8 minus, this is again this one, this is negative x. So 8 minus 2 plus 2, that becomes 0. So you'll find x minus 2, and other I can write x square and then minus 1, and we'll find here nothing, x is not there because already 2 square is here. So you factorize like 12 x minus 2 x minus 1 x plus 1. Please note, in both the examples, this one and preceding one, something beautiful was there, that although f I cannot factorize, that's the whole point. In first one k is there, so I anyway can't do anything. Second one, all coefficients are known, but still I can't factorize f. But f prime is really good, I can factorize f prime. So f prime is this one. So now roots of f prime are arranged in the number line, that is negative 1, 1 and 2. They are roots of f prime. Roots of f prime. Now we know that when we calculate roots of f, we want, so we'll say that now we just need to get the sign of f at these points, because we know that in each such interval, there can be at most one root of f, means either no root or zero root. So let's calculate the sign, and don't forget you have got here negative infinity and infinity, which you cannot see. So now f of x was 3x to the power 4 minus 8x cube minus 6x square plus 24x plus 1. Let us check. 3x to the power 4 minus 8x cube minus, yes, it is. Now I want sign of it. So value of x and then values of fx. And so negative infinity, negative 1, 1 to infinity. Here value is infinity, here infinity. This is positive in positive. F negative 1, f minus 1 if I write, then it is 3 and plus 8 minus 6 plus 24 plus 1. Obviously it is positive. I'm not interested in the value itself. All I need is sign or something. So it is negative because we are putting x equal to negative 1. So this number, in fact, this number is just negative because x is minus 1. And so this is negative. So this is negative. F1. If I put F1, then 3 minus 8 minus 6 plus 24 plus 1. It is seen to be positive quickly. So this is positive. If I write F2, then F2, of course, you have to compute again. So your F2, let me calculate F2 again. So your F2 is little big calculation, but we have to do it. So this is 3 into, so 3 into 2 to the power 4 minus 8 into 2 cube minus 6 into 2 square plus 24 into 2 plus 1. So that gives you 48. So that will give you some other thing. So let us calculate this. So we are getting this as 48 minus 64, then minus, this is again, you will get some answer. So let me quickly do it. So you will get 24 and then plus 48 plus 1. So this happens to be positive, and so this again happens to be positive. So signs are negative infinity, of course, positive because power is even. Positive infinity, again positive. Then negative, positive, and positive. So negative, positive, and positive are there. And so if this is the kind of case, then we know that this equation has exactly two real roots. Between these two, no real root because sign is positive. We said at least one or none. So it is none because sign does not change. So it means here you have got one root in minus infinity to minus 1, this one, and other root you have got in minus 1 to 1. So these are the two intervals in which f has got roots. Other two roots are real, imaginary. Means f has got two real roots. We have also looked at intervals. So two real roots and two non-real, we can say, or imaginary, also is a loose word. So two non-real roots. So that's the conclusion for it. Let me do one application based on applying Rawls theorem to some chosen function. Means that suppose you have got px as a polynomial. So suppose you have got, or any polynomial or function also is all right. Let px be a polynomial. Now p of a is 0 is p of b, that is given. A is not b. You can take a less than b or positive, that's not matter. And now you are saying that prove that, so you have to prove that there exists c that belongs to open a comma b such that p prime c plus alpha times p of c equal to 0 for every alpha belong to R. Means you are saying that if p is a polynomial, I do not know what polynomial that is. It may be any degree. And in fact, result holds for function also, but let's do a polynomial. So pa is 0 is pb. So prove that there exists some c element of ab, open comma ab, such that this equation p prime c plus alpha pc is 0 for every alpha belongs to R. Now, there is something called integrating factor. When you see something like f prime x plus alpha times fx, think of this, we did in one of lectures, think of multiplying by e to the power alpha x. That comes from differential equation, but still it is correct. So e to the power alpha x times f prime x, at least you can quickly check, this equals d by dx of e to the power alpha x times fx. That's what makes it work. That this identity that you get, or this beautiful thing, e to the power alpha x f prime x plus alpha x, this is d by dx. So you can quickly check it. When you differentiate using product rule, you get e to the power alpha x times f prime x plus fx times e to the power alpha x by chain rule and times alpha. And so you are back here. So you get this kind of thing. So I will construct this alpha pc. So I will construct one polynomial qx or some function qx equal to e to the power alpha x times px. This is my construction. So construct a function. It's common for mathematicians to construct auxiliary functions to serve their objective. So I construct, I define, I set up. So I construct some function. Qx is this. Now q of a is e to the power alpha a times p of a. So q of a is again 0 because pa is 0. And similarly, q of b also is 0. So qa qb is 0. Because p is differentiable and e to the power alpha is differentiable, so product is differentiable. So your function q is differentiable on whole of R, and of course then continuous also whole of R. So Rawls theorem applies. Means now you have got a function q which is continuous on R and differentiable on also R, and qa equals qb equals 0. That is okay, bonus. I only wanted qa equals qb. It is 0 also. So in a way we can say n be are roots of it. Then there would be some c belonging to open AB. Something will exist such that q prime, derivative of q at c will equal 0. So let's find derivative of q. So q prime is derivative is just this one. In fact, that was the reason you created this one. It is backwards reasoning. So that derivative q prime x e to power alpha x, and then p prime x. So p prime x and plus alpha times px. Now we know that there is by Rawls theorem. So by Rawls theorem, there is some c such that q prime c is 0 implies e to the power alpha c into p prime c plus alpha pc equal to 0. But this number is never 0, and so it must be the case that p prime c plus alpha pc is 0. It means there is some c such that derivative of p at c plus alpha times the value of p at c, if you sum them up, they will become 0. That's what was to be proved. That you have to prove that there is some c that belongs to open AB such that p prime c plus alpha pc equals 0 for any alpha element of R. In fact, if alpha is 0, then it is plain. If alpha is 0, it is p prime c 0. That is definition only, or that is the conclusion only from Rawls theorem that you get directly. But this proof works even if alpha is 0 or not 0. It does not branch out. So this proof works for each possible alpha. So for every alpha, we have proved this. Now I will tell you two more theorems, which are of course derived by Rawls only, but they have got different names, and they also are important because mostly they are used in other things. So one is called Lagrange's mean value theorem. Lagrange's mean value theorem means I will call LMVT or Lagrange's. So Lagrange's mean value theorem, LMVT, and other is Cauchy's mean value theorem, that is CMVT. That of course we will do just afterward. So this statement is exactly now this one. F AB to R is a function. F AB to R a function. The way it was. Hypothesis, that is fine. F is continuous on AB, closed interval. F is differentiable or derivable. F is differentiable on AB. This is open, this is closed interval. This is open, I emphasize, closed and open. And third, nothing is there. In Rawls it was f of a equal to f of b. That we are not taking now. So just two conditions, just two. This is not there. So if f is continuous on AB and difference on AB, then there exists C that belongs to a open a comma b such that fb minus fa upon b minus a is f prime of c. Means they are saying that then there is a point such that the derivative equals this quotient fb minus fa upon b minus a. Means this is the slope of chord AB. So this is like that anything, suppose you say like this, there's a curve here. So you are saying that this is your A and f of A geometrically. This is your B and f of B. Now we don't require that FA equals FB. Means heights of these 2 points above x-axis may be different. I don't care. Rawls, we cared it was same. So this says that, okay, so this is some line. Its slope is FB minus FA upon B minus A. So they are saying that there is a point C on the curve. The curve is same, continuous and differentiable except endpoints. So you are saying that there is a point on the curve on the graph of F such that the tangent at f to that point, so tangent at some c to f is parallel to chord AB. So this tells you geometrically this only, that the slope of tangent at some point along the curve must equals the slope of chord AB or secant AB. That's what geometrical meaning is. Of course, if you put FB equal to FA, if you put f of B, if you put f of B equal to f of A, you can recover Rawls theorem. So Rawls theorem, of course, can be derived from Lagrange's theorem. And then what is curious is Lagrange's also can be derived from Rawls theorem, but applying on some different function. That also is important. But for now, we are not doing that proof. We are more doing the application part. And then other is called Cauchy's mean value theorem. So that is CMVT. It talks of two functions instead of one. So you have got let fg ab to r be functions such that first fg r, they are both continuous on closed interval ab, closed interval ab against same closed, and f and g, they are both differentiable on open interval AB. So that's an open interval AB. And then third, I will write a condition. Third, g of x, g prime of x is not 0 on AB. AB open means g prime is never 0. G prime means derivative of g is never 0. Then there exists C that belongs to A comma B, such that fb minus f of A upon gb minus g of A, that equals f prime c over g prime c. Let me remark that I did not tell you that gb is not ga. I just told you g prime c is not 0. In fact, that will follow, because you are saying that g prime c is never 0. So if ga equals gb at some, if ga were equal to gb, then by Rawls theorem, between A and B, there would be some point C such that G prime C is 0 or G prime alpha is 0. But no, given G prime C is never 0. So GA is not GB. So this I need not write. This follows from condition on G prime X. So derivative of G is never 0 on the interval open A to B. So this is well defined. Other version is that don't write this third one. Then you can say after here directly that there is some C element of AB such that FB minus FA times G prime C is GB minus GA times F prime C. Now no need to mention about G prime, because if G prime is 0, then all right. If G prime C is 0, then GB equal to ZA. That is, of course, known, or F prime C is 0. So it means that we can write in this form, or if you want in this form, if you're writing in the form A over B, division form, then in this form, you have to write condition on denominator, obviously. So you write G prime is never 0. This need not write, because this will follow that GB cannot be equal to ZA. Because if GB are equal to GA, then of course this is 0 is not happening, will not happen. So this will ensure GA is not GB. So these two forms you use in Cauchy's. So Lagrange and Cauchy, these two also form really important part of it, Lagrange or Cauchy. So one example we can take to illustrate them is this. This has two advantages. So if 0, 1 to R be a function, continuous on 0, 1 given, and f is given to be differentiable on 0, 1 open. So differentially demanding only on 0, 1 open. So differentiable. Then you have to prove that first that f1 square minus f0 squared equals 2f alpha times f prime beta for some alpha beta that belong to 0 comma 1. That is one aspect. And second part is that f1 square minus f0 square only equal to twice f alpha f prime alpha for some alpha that belong to 0 comma 1. Of course these two are not same alpha, so it means you are saying like this, that you want to prove existence of two numbers alpha and beta such that f1 square minus this is 2f alpha times f prime beta for some alpha to belong to 0 1, and here you just want one number such that this square equals this number 2f alpha squared. First solution to part A, that makes you of two things. One is intermediate value property for continuous function. You are saying that f0 f1 is defined, so f0 plus f1 by 2 is one value that the function takes. So if function takes the value f0 and it takes the value say f1, it may be small also, it takes these two values continuous function. It means it will take every value in between, in particular their average. So f0 plus f1 by 2 is of course taken by some function by some point. So that is say point f of alpha element of 0 comma 1, means one part coming from part A or part 1, one thing is coming from that the number f0 plus f1 by 2, because this lies between f0 and f1, and so there is some alpha by IBP such that function takes this value. So f0 plus f1 equal to twice f alpha. Now apply Lagrange's LMVT to f on 0 comma interval. On this interval you apply LMVT. So on this interval f is continuous and open it is differentiable, that is given. So f1 minus f0 by 1 minus 0 should be f prime of beta for some beta, for some beta belong to 0 comma 1. So it means f1 minus f0 equals f prime beta. If I multiply these two numbers both, so you will get that f1 square minus f0 square is 2f alpha f prime beta for some alpha beta belong to 0 comma 1. We can't determine where they are, but some 0 comma 1. So it means you approved the first part, that this is true, that this does happen. So we used IVP also, and then we used plus mean value theorem. For the second part, we'll use LMVT, but not on this function, but some different function. So that different function is, that motivation will come. I will write g of x equal to fx square, this function. Why? Because see, I want f alpha, f prime alpha. So like this tells me if you have something like u prime, so this is nothing but d by dx of u square, no, to u prime and half other things that is all right. So this, so I'll apply this function gxf. Now this again, this function is also on 0 1 continuous, on 0 1 open differentiable, because f is there, f square also will be there. So apply LMVT to g on 0 comma 1. So g1 minus g0 upon 1 minus g0 is equal to g prime c, that is g1 f1 square minus f0 square, so f0 square equal to g prime c. So g prime x is 2 fx into f prime x. So you will get here that this is g prime x, so this is 2 times fc into f prime of c sum c. It means that f1 square minus f0 square is 2 times fc times f prime c. This c can be identified, c to be identified with alpha, means there is some alpha such that f1 square minus f0 square is 2 alpha is or here it was 2 alpha f alpha prime, both are f prime and alpha, both are same point alpha alpha. Here alpha and beta are different points, so we get again same thing, 2fc, so c is just alpha. If we think of some more things of application, it is like this, that again f01 to r be a function continuous on 0 1 closed, and f is differentiable on 0 1 open. These two are there. And given f of 1 is 0, f of 1 is 0, you want to prove there exists c that belongs to 0 comma 1 such that c times f prime c plus fc is 0. Again, this calls for constructing some function. So we construct some function. So if you construct these functions, let's take the motivation. So you have to prove actually c f prime c plus fc is 0. Now think of c as x. So it is x f prime x plus fx equals 0. You know that this number, this x of as d by dx of x times f of x, because this, when you differentiate, you will get x f prime x and plus fx you will find. So let's do this one. So if we consider the function gx is x times f of x, then g of 1 is f of 1, which is given to be 0. f1 was 0. Look, f1 is 0. f0 did not say anything for good reason, because g0 is 0 times f0. f0 we don't know, but it is 0 here, so it is 0. So we know now g1 and g0 we know. And apply Rolle's theorem. It's time to apply Rolle's theorem. So Rolle's theorem on g function, because continuous. So you will write that there is some c that belongs to 0 1 such that g prime c is 0, and gx, because gx was x fx and we constructed it, so g prime x is x f prime x plus f of x times 1. So x f of prime x plus fx. So it means g prime c is 0. That gives you that c times f prime of c plus fc is 0. So you have proved it. So you have proved that if f is such a function, continuous on closed interval, differentiable open interval, and f1 is 0, then there is a c such that c f prime c plus fc is 0, because you're constructing some function, and after construction, this construction motivated was this one, by looking at this expression, that this can come from this one. So think of c as x. So then you construct this one. G1 f1 they give, all right. F0 not given the problem, not given, but no problem, because f0 is not known, but anyway 0 is there. So if g0 is 0, and by Rolle's theorem on g you will find that there is some c such that g prime c is 0, gx is this much, g prime is this much, and so c times this plus fc is 0, and so we are done. So in effect, Rolle's theorem, Lagrange mean value theorem, and Cauchy's mean value theorem, they all are important part. Most important is Rolle's theorem. And so in IIT you will find every year they'll ask you questions based on Rolle's theorem or Lagrange's or other things. So that's all for now today. Let me stop sharing. Okay, so that's all for today. Let us connect